Hi everyone, my name is Gabriel. I'm currently the head of advanced imaging at the Gulbenkian Institute in Oeiras in Portugal. I've also been teaching bioimaging for the last 12 years at Ciencia University of Lisbon. I hope this webinar finds you in good health and spirit in these troubled times we're living, and I want to thank you for taking time to watch this webinar, and also thank Claudia and Susan for giving me the opportunity to present this work. And these beautiful images that we have been obtaining with this still fairly unknown technique, which I believe has a lot of potential and should get more attention from cell and developmental biologists. I want to start by giving you a brief overview of where optical tomography fits in the landscape of multiple optical imaging techniques that we have these days, which can range from nanoscopy, the observation of individual molecules, all the way up to overstepping already in the medical field of imaging. Now, typically, most of you, I believe, are microscopists, are familiarized with samples on this range, microscopy range, with magnifications up to 60 or 100x, where you can see, with a fair amount of detail inside even individual cells. Now, if one cell is represented as this little dot on the screen here, you have this whole range of samples that we can now these days actually put in a microscope and obtain fairly detailed information, even three-dimensional information of. Confocal is probably the most common technique that most of you are familiarized with and use probably on a daily basis. And you know that with confocal microscopy, you can generate three-dimensional images, so to speak. In fact, you don't generate three-dimensional images, but you obtain optical slices of a three-dimensional sample through confocal microscopy. If you're lucky to have a 2-photon setup on your lab, you know that you can actually image deeper, so get a larger chunk of three-dimensional tissue where you can obtain information from. If you're a developmental biologist, very often this isn't enough. For example, if you want to image a whole zebrafish developing over the course of 24 hours, the whole zebrafish is 10 times larger than you typically can fit with high quality on the field of view of a confocal microscope. So you end up resorting to other techniques, relatively recent techniques. Now, this range of sample sizes that falls in between the typical microscopy and up to the macro or medical imaging field is become known as the mesoscopic scale, or mesoscale and mesoscopic imaging. And there are many techniques, but the two most prominent techniques that have addressed the challenges of these large samples have been light sheet, which I'm familiar most of you have already seen, heard of, or even used, and optical tomography, which extends even a little bit beyond the range of most light sheet systems. Now, what are the samples that you typically want to image with light sheet or optical tomography? As I said, very large samples, like a whole zebrafish embryo, or even larger, like a whole mouse embryo, here represented by this little image here, or a sample that is about 6 millimeters long. Now, these actually dwarf in comparison to the size of this avian embryo that you see here in the back. It's actually more than halfway through development. It's huge, it's very large. So you would never put this on a microscope and expect to see with detail the whole sample. And that's where optical tomography really excels, is in providing you with the possibility of obtaining these fairly large images. Now, I've already alluded to the fact that we're talking typically about three-dimensional imaging using optical slicing, as you normally use it, for example, confocal microscopy. The paradigm for three-dimensional imaging in medical fields and even in optical microscopy is still pretty much that you image and handle images of large volumes as a series of optical sections. This is known generically as tomography. The word tomography is more common in medical imaging and not so much in optical microscopy, but in fact, confocal microscopy, light sheet microscopy are a form of tomography. Now, you can obtain these tomographic series or Z stacks of optical sections as we normally know them in optical microscopy in both a direct and an indirect manner. If you're illuminating the whole sample simultaneously, as you normally do with wide field microscopy, you don't really get optical slices because you're seeing everything, including the narrow depth of field where the optical system is providing you with a maximum contrast, but also everything that's out of focus. And it's extremely difficult to obtain a tomogram when you're doing imaging in wide field illumination and detection mode. Now, you can be a bit more precise, more selective in how you either illuminate or detect your signal from your sample, and that's what you do with confocal microscopy, where you kind of selectively illuminate point by point the sample, and you're very selective in how you detect the light that emanates from that point that is swept across your sample sequentially. The disadvantage that you know of confocal microscopy is that you're still illuminating the whole sample, and you're subjecting all of the cells and all of the tissues, even the ones that you're not imaging, to very intense irradiation, which is not very healthy. Light sheet microscopy was a great revolution, started 15 years ago, in that it completely changed the way that we illuminate samples. It's a selective method of illuminating your sample, which allows you to detect, image, and generate and detect fluorescence only exactly on the optical slice that you're trying to image. And that allowed developmental biologists to observe embryos by much longer periods and in much better health conditions than it was typically possible. There was a huge hype, rightfully so, about the development of light sheet microscopy in the last 10 years at least, which kind of overshadowed a little bit the development of optical tomography. Now, just to reiterate again what optical tomography and where it fits, with wide field illumination, you can actually also obtain optical slices. And typically you need to do that by computing, by using some form of computer power to derive optical slices from the raw images that you obtain. Wide field deconvolution is probably the most common method, which I'm sure most of you are familiarized with. You can obtain wide field images, and if you're fairly confident about your knowledge on the point spread function of your system, you can actually guess or derive optical sections, but that has a limited depth. You cannot really go very far, and you won't see normally deconvolution applied to imaging large embryos. The other technique that I'm talking about today, which also relies on computing optical slices from a wide field image, is computed tomography, or more commonly known as optical projection tomography. It's akin to medical imaging, and we will see in a moment how it operates. And this is where I'll be concentrating the rest of my talk today. So a few years ago, we started a project at the Gulbenkian Institute to develop a fully open source light sheet microscopy. And now I joined the group and started collaborating with the group of Nuno and Emilio back then. And we decided that we wanted to get a system that was not just fully open source, but was also capable of doing not just light sheet microscopy, but also optical tomography, which we believe were two very interesting techniques back then that required further development and opening to the community. Now, as most of you probably know, there was another project going on at the same time called the OpenSpin project. And we just found out as we were working on this that they were also working on the same project and even had the same name for the technology. So we kind of joked and came up with a different name called OpenSpin microscopy instead of OpenSpin microscopy, as it's fairly well known and fairly well documented on the internet. The term spin here refers to the fact that we're focusing on the high precision of rotation of samples that you could do with this, in this representation here, a fairly simple setup, but which actually allowed you to do optical tomography. Now, where did the optical tomography come from and what does it do? What kind of problems does it address? Well, if you want to image large samples, as I've shown you, you can use some kind of small animal imager, but you are not going to get three-dimensional imaging most of the times, which is what we want. You have destructive techniques like episcopic tomography, where it actually physically slices the sample slice by slice progressively, and you can obtain a three-dimensional reconstruction, but the sample is gone by the end, and it's fairly technically complex to obtain. Or you can resort to these very expensive, cumbersome techniques like micro-MRI or even a synchrotron facility, which cost in the ranges of millions of euros and thousands of euros an hour to operate. And they're very low throughput. You're lucky to get one sample every day. The other alternative, which is typically not available to microscopists and developmental biologists, is a micro X-ray CT scanner, which you will find very often in engineering departments. The problem of micro CT scanners is that they are not designed to operate with transparent samples, with biological samples that don't have radio opacity. If you put an embryo inside of one of these machines, it's too transparent for X-rays and you won't be able to see anything. Now, there's beautiful work done with micro CTs out there, which requires basically preparing the sample with some kind of radio opaque chemical, but it's still not it's not very common or an easy technique for most biologists. Thinking of that, James Sharp developed and then later created a company that created a optical tomography scanner for light instead of X-rays. Now, how does it work? Well, in medical imaging, if you want to obtain information about the inside of the human body or any other huge sample, you need to resort to X-rays. Biological materials are transparent to X-rays. As it goes through the biological material, you can detect an image on the other side and basically get a shadow image. If you rotate the detector and the X-ray source around the object, the person, you can obtain images from all the angles and then compute what is a slice, a computed slice. The computer generates this. Now, the process is known as generically as back projection reconstruction. And if you see here this image, you can try to create something kind of similar where you have a sample in front of a camera that is rotating and you're acquiring images from all the angles. You use the exact same algorithms to reconstruct this image line by line, as you see here in this movie. If you go line by line, you can actually reconstruct this, each one of these axial levels or planes along this movie of the sample rotating, and then generate optical slices. The technique is pretty much the same as using medical fields. Now, James Sharp first developed this in 2002. And as I said, it was a company that lasted for about a few years up until 2012, I believe, 2010 or 2012. And then the technique was no longer available. Light sheet microscopy came of age. People started getting really excited about light sheet microscopy, and they sort of forgot about optical tomography. And it's a pity because, as I will try to convince you today, it generates really, really interesting images, and it's far more accessible to build and operate and maintain than a light sheet microscope. Now, one of the great things about light sheet microscopy is that it brought huge developments to the field, and it's still ongoing right now. And it's becoming more and more challenging to biologists to get their hands on the latest high-end light sheet microscope, or even choosing which one is the best for their research, because there are so many options these days. Optical tomography has had a fair amount of development, but not as much hype as light sheet microscopy. And as I said, it's much simpler to get your hands into, and I will try to convince you that it's worth your time. Now, as we were developing the OpenSpin project, where we gave everyone access to blueprints and even software and the hardware instructions of the OpenSpin microscopy project, we also started developing the OpenT, which was sort of a spin-off of the OpenSpin project, a simpler version of a setup that would do just optical tomography. And you can find this information online as well. You can contact me and I'll direct you to where you can find all of this information on how to build your very simple optical tomography setup. With just a few 2,000 euros or even less, you can build a fairly usable and very interesting setup. You don't need lasers. You don't need very expensive high-end cameras. You can even use an industrial camera, very simple industrial camera as represented in this diagram here. You can build your own illuminator. And in this case, you use simply an Arduino controller to run the whole setup. It's fairly simple. So is it worth your time? The other thing I want to tell you about is the fact that very often you don't, especially if you're dealing with late stage embryos, you don't want to do very high magnifications. In fact, you may actually want to do demagnification. You want to image something that's larger than your chip, the chip on your camera. So very often in optical tomography, instead of using 1, 2, 4x, 10x magnification, as you do with light sheet microscopy, you may actually use less than 1x magnification, like zero. Like in this case here, we have a demagnifying telecentric lens, which provides a 0.3x magnification. Now, as long as the chip on your camera has lots of pixels and your optics are good enough to fill those pixels with actual information, then you're getting detail of something that's large, but you're getting detail of small structures inside something that's fairly large. Now, the other thing which I believe I failed to mention yet is that optical tomography for these very large samples relies on your ability to see through the samples. Just like with X-rays, you have to see through the sample, see what's inside, and reconstruct the anatomy from the inside. Also, with optical tomography, the samples have to be fairly transparent. Now, this is not a requisite only of optical tomography. Light sheet microscopy will also not give you details inside a sample that's not transparent enough. The same thing for confocal or even two-photon microscopy. The illuminating light needs to go through the sample and needs to get inside for you to actually see what's inside. With optical tomography, this is extremely important. You actually have to see through the whole sample in order to reconstruct a proper optical section later in the process. So that's one reason why typically you only see optical tomography applied to dead, fixed, and cleared samples. But if you get proper clearing and fairly well-mounted samples and cleared samples, you do get amazing results, even with a fairly simple, much simpler than this setup than what you're seeing here in this image. Now, another interesting thing about optical tomography is that you can operate both in fluorescence mode, as most developmental biologists are used to, from using confocal microscopy, fluorescence microscopy, or, for example, even light sheet microscopy. But you can also operate in bright field mode. Now, because we normally want to do three-dimensional imaging, on confocal microscopy, you cannot do three-dimensional imaging using transmitted light, even though you can image with transmitted light. But in fact, with optical tomography, you can use also transmitted light, as in this example here, and with that, obtain optical slices, compute the optical slices, as long as the sample is transparent enough. And here, this rabbit embryo is shown inside an agarose block after it was rendered transparent by a tissue clearing technique. Typically, we use a combination of benzyl alcohol and benzyl benzoate, we call BABB, for clearing these and imaging these samples in optical tomography, but there are many other techniques for clearing tissues these days, which are being explored and which might have applications in optical tomography as well. After you've obtained the series of optical sections by computation, as I said, you can then reconstruct three-dimensionally and do these 3D renderings of your Z stack. Now, how good are these images? Is it worth it to build this thing? Well, this is an example of a fairly large, but still small sample. It's a 6mm mouse embryo at, I believe, 14 days of development, a little bit beyond halfway through development. And it's probably not quite clear to you at this point, but one of the advantages of optical tomography is that these images are isotropic. You can get the same resolution no matter which angle you look from. And if you've tried to look at a confocal stack from a different angle, you probably have gone through the frustration of seeing, oh, it's a lot worse. I can't see the detail so well. With light sheet microscopy, that can be addressed by imaging from multiple sides and doing what's called multi-view reconstruction, where you merge different views from different angles of the sample, and with that increase the contrast and the detail on your volumes. But that's computationally cumbersome. It takes quite a while to do, depending on the size of your sample and the level of resolution that you're trying to achieve with light sheet microscopy. With optical tomography, you don't have to worry about that. Because you're imaging through all of the angles of a sample rotating, you can see it from all of the angles. That's the only way you can get an optical slice, is by actually imaging from all the angles. So when you reconstruct it in 3D, you still have to go through a computational process, but when you do that, you obtain a data set that's isometric. Now, not always easy, not always beautiful with optical tomography, and in this case, you can actually see that there's some artifacts as well. For example, some edge artifacts, or there seem to be some rays pointing in this direction here. These are artifacts caused by either something that was very fluorescent inside your sample, or very dark, where we couldn't get much information from, or bubbles, air bubbles in your sample. Again, keep in mind that this is a problem for any technique, even light sheet microscopy. Very often you don't realize this until you've reconstructed it in 3D. With optical tomography, once you've reconstructed it in 3D, you realize that these artifacts are in there. And if you don't use this technology well, you end up getting lots of artifacts. We'll get back to that later on in this talk. Now, we kept on pushing the limits with the optics and the amount of information we can get from this, and we decided to do something a little bit larger, 6 times larger, actually. This is a pup, mouse pup after it was born. We were, at this point, getting a 4-megapixel camera, and we got these amazing results. You don't always get these amazing results, but this one is actually stunning. It's incredible how much detail you can get, and bear in mind that you're not really seeing the full resolution of this. This is a 6 gigavoxel data set that we obtained from this 3.6 centimeter long mouse pup. And the resolution that you obtain with this is around, if I'm not mistaken, about 10 to 20 microns, actually about 10 microns of resolution, which is, not cellular resolution, but, tissue level resolution. This is 3D virtual histology. You don't have to section the embryo. The embryo is still sitting in our lab in a flask. We still have it, and every now and then we try to image it again for tests. But in this case, this embryo was actually very, very transparent. The tissue cleaning worked really well, and we were able to obtain these amazing results. So we decided, well, how far can we go? And in fact, the extent of where we could go was put to the test when a colleague from Australia called us and said, we have this bioptonic scanner that cannot scan the whole series of quail embryos, and we would like to do an anatomy database that includes images from all of the stages, not just the very early stages, but all the way up to full development, which it's about 16 to 17 days. So they had to stop by about the 9th day, I believe, because it was simply not possible to put the whole embryo inside the very small cuvette that you had on these old OPT scanners. And I had built this fairly large cuvette, or acquired this very large cuvette for my scanner, and I was just, testing how big a sample I could put in there. So we were actually able to image really very large, all the way up to 4 centimeters long, which is the full term. And now we're really talking, if this is a zebrafish embryo, this is a dwarf compared to these giants. And keep in mind that you do obtain images that contain all of the information inside these samples. So these are already 3-dimensional reconstructions done from the images. In this case, you see here again a few artifacts obtained from the fact that there were bubbles in this air bubbles in the sample when we mounted it. And then accidentally I was given this rabbit embryo, which I don't really know the stage. It's probably approaching the term. And that beat my record. That went up to 4.5 centimeters. Really interesting. I had back then I had no idea that anyone had ever tried to image this. And again, keep in mind, this gives you all the anatomical information, all the detail inside this rabbit embryo as well. To obtain an image like this on a 2,000 euro OPT scanner takes about 1 hour. Probably even less than 1 hour these days with the GPUs that we have, with the graphical processing units that we have in most computers. So how far can we go? And again, by luck or serendipity, I was also given this duck, probably very close to full term, which we were able to image. and actually you have the setup in here where we used to image this, and now we're talking about 10 centimeters, a full 100 millimeters. These are really giants that you put in a microscope. And more recently, through a collaboration with a colleague, we actually started looking at these shark embryos. And this is one of the later stages that we've done. It's actually like a day after being born. It's more than 10 centimeters long, actually. And you can see that with the optical tomography technique you've been seeing here in this movie, you can see all of the anatomical details inside with the resolutions down to 10, 15 microns. You can see here, you don't get that much resolution from looking at this image, but I will show you in a moment the level of detail you can get when everything works beautifully. Now, for developmental biologists, optical tomography has another interesting lure, is the fact that you don't even need, and I mentioned this before, you don't even need to stain your samples. You can actually use just transmitted light, as long as there's a little bit of contrast, you can always generate a three-dimensional image. So if you're using non-model species, bizarre species that where you cannot easily get transgenics expressing fluorescent proteins, you can still get a three-dimensional image from them using optical tomography, whereas it would not be possible to get 3D images, or not easy at all to get 3D images using, the conventional confocal, two-photon, or even light sheet microscopy. Developmental biologists often also use stains like these bone and cartilage stains to look for developmental defects. And you can actually image these as well. This is an actual image of one of our versions of optical tomography scanning, where you can look at a chick head stained with Alcian green and alizarin red to look for cartilage and bone. And if you can obtain images from all of the angles, if it's transparent enough that you can see through it, you can reconstruct it in 3D and then obtain measurements from this in 3 dimensions. The alternative to doing this would be to use, for example, a synchrotron facility, which, every sample will cost you thousands of euros and days of imaging. It's extremely cumbersome, as I said before. With less than 2,000 euros, you can build, in fact, in some cases with as little as 1,000 euros, you can build a setup that will allow you to do this imaging. Now, just give you another example of another project that we've worked on. There was this challenging toadfish here in Portugal, and a group from the University of Lisbon came for our help, because it was, it's possible to obtain images on your stereoscope with this, but you cannot actually see inside and see the anatomical details. And they were actually interested in the development of hearing and sound production abilities of these toadfish. And just to give you an example, so if you put this on a fluorescent stereoscope, this is what you see. If you put it on a confocal macroscope, we're not talking a macroscope, you get a little bit more detail. Obviously, you can do some form of three-dimensional imaging, but you're using very low numerical aperture objectives, so you're very limited in your ability to do direct optical slicing. With optical tomography, you compromise the resolution a little bit, but because you can actually do isometric optical slice reconstruction of the whole, even 5 millimeter or even 3 centimeter long embryos, you can actually get a lot more detail than you get with a confocal macroscope. And we demonstrated that in a publication a few years ago. And this here is just represented some of the stages that we were able to image, from 1 month to 1.5 months to 3 months, where there are these gigantic 2.5 centimeter long animals already freely swimming and producing sounds. Like, as I said, the group was actually interested in the development of the hearing apparatus and sound production apparatus. So this image here just shows you the amount of detail you can get from those images that you've seen before, where you can reconstruct the swim bladder, measure its length, its volume, everything, including the hearing apparatus inside the embryo. And you can even generate something really cool, which is a 3D PDFs that you can put with your publications. And because the images are isometric, you can rotate them from any angle and you always get the same kind of resolution. So it's very precise for making measurements that don't lose quality as you rotate the sample from sideways, which is what would happen to most of the cases where if you're using a macro confocal, or if you were trying to do Thailand stitching on your regular confocal or two-photon microscope. Now, more recently, we decided that we wanted to continue pushing the limits of the sizes of samples that we can image with this setup, but not lose track of the fact that we don't just want to image large samples, we also want to image details inside these large samples. And, you know, optical tomography and light sheet microscopy have, at some cases, been portrayed as being competitive techniques. They're not. They're really not competitive techniques. They don't exist to compete with one another. They're complementary techniques. And in that respect, it makes perfect sense to actually have a mesoscope that can do both light sheet and optical tomography. Whereas, for example, you can obtain a whole image of a whole animal, of a whole embryo during development using transmitted light, but then just focus on a specific group of cells that you're interested in, or an organ or a tissue that you can follow through fluorescence microscopy if you have a transgenic expressing just on your tissue or cells of interest. And that's what we've been working on now with the help of Ocean Globes, who recently joined the lab by using this dual setup. So the sample sits in here, and you have a 4 or 10x magnification light sheet set up on this side with the lasers illuminating on this plane here. And then on this side, you have the stereo version of the optical tomography side, or arm as we call it. And the sample is suspended by this motor, is rotated, so you can do multi-view reconstruction using light sheet microscopy if necessary, but in most of the cases what we're aiming for actually is not having to do multi-view reconstruction, because you can get three-dimensional reconstruction of the whole embryo using the optical tomography setup. And as you see, with optical tomography, you can use small, cheap cameras, whereas with light sheet microscopy, you typically have to resort to, you know, high sensitivity cameras, more expensive cameras. And here, just representing on the tip of this, of the snout of this shark embryo, you can see that you can get, you know, fairly good resolution. With optical tomography, these are images of optical tomography, and they're fully isometric. No matter which angle you look from, which plane you're trying to reslice your sample, you get always the same kind of detail. For more detail, we can resort to SPIM light sheet illumination, and then you get even more detail, and that's what we're working on. The challenge then is to actually combine the two images and keep them on the same data set, so to speak, which you can still do using Fiji these days, and Big Data Viewer, for example, or other software solutions. So that's pretty much what we've been working on. I would just like to end by highlighting the strengths and the limitations of optical tomography to try to convince you whether you should or you should not get into it. As I said, it's very easy and cheap to build and implement. There are multiple open source solutions out there. The one that we developed called OpenT is just one of them. It's much easier to operate and maintain than a light sheet microscope or even an open SPIM or a macro SPIM. Even though these have different applications, once again, I don't want to portray optical tomography as a competitor, but if you're venturing for the first time into building something in your lab, and if all you need is, you know, low magnification and not high resolution cellular, subcellular level information, if all you want is to reconstruct organs in 3D on a large embryo, maybe optical tomography is just enough for you. And it's much easier to build, as I said, and operate. It doesn't require lasers or complex optics or even sensitive cameras. It has this added value of allowing you to do 3D imaging using bright field. So you don't have to do staining, which can be fairly challenging on very large embryos, or even producing transgenics with fluorescent proteins. Just autofluorescence is enough, and if you don't want to use autofluorescence, even bright field is enough. So in some cases, bright field might actually be more powerful than doing fluorescence, because if you're doing red-shifted illumination, you can actually image deeper and see details deeper into the samples. I've also mentioned this great advantage is the fact that you have inherently isometric reconstructions. No matter which angle you choose to see the slices from, you will get the same quality, which is not true of, you know, even light sheet microscopy, unless you do multi-view reconstruction, and multi-view reconstruction is cumbersome. It takes quite a while. It's data hungry. It requires very fast computers, and very often you don't get real isometric reconstruction from the samples. It's fairly complex to do that. So the one thing that is typically seen as a disadvantage of optical tomography, it's the fact that you don't get instant gratification, you don't get immediate optical slices. If you consider that you have to do multi-view reconstruction with light sheet microscopy for these mesoscopic samples, so that also is computation, that also requires time. So in a way, the fact that you get immediately asymmetric reconstructions can actually also be seen as a strength of optical tomography. You're done, you reconstruct, but you're done. Now, not everything is easy. Obviously, there are some limitations. The fact that you need to see through requires that you have to kill things and make them transparent. And because you have to see through the whole sample, typically you have to resort to low numerical aperture objectives, low magnifications, which don't give you the high cellular and subcellular resolution, which you might or might not require. It also severely limits your ability to capture photons. So you very often resort to long exposures and you have photo bleaching, and that is a problem that you need to address occasionally with optical tomography. Now, if you don't use it correctly, it does generate lots of artifacts, and you have to do fairly familiar with optical microscopy, with image processing techniques and applying image processing techniques to avoid some of these artifacts. But bear in mind, that's reality also if you're doing mesoscopic imaging with spin or even confocal or two-photon imaging. Now, the one thing that takes people off from trying to do optical tomography is the fact that it requires these filtered back projection reconstruction to obtain the optical slices. But we've been trying to convince people that this is actually not that difficult. I'm a biology researcher. I didn't have computer training, computer science training, and I was able to figure this out with the help of colleagues. So if you do want to venture into this, you can start by searching our publication in 2013. There's also now another open source project called OPT-ical, which is fairly easy to use as well if you want to implement and learn how to reconstruct things in 3D with optical tomography. And there's a new chapter coming out. We just had a new chapter that's coming out on a book very soon. So contact us if you want more information. This chapter actually describes every step, and it provides you with places where you can get the software to make these three-dimensional reconstructions. So I hope I was able to convince you that optical tomography is interesting enough that it might be worth it to look into. And I just want to finish by thanking the funding that made this project possible, and also Nikon, who gave us a prize for this beautiful image of the quail embryo that you saw in the beginning of the talk, and also many of the collaborators who have given us samples and provided us with challenges for these images, and some of the people I've had the privilege to work with in this project and other projects, namely Nuno Moreno, Nuno Martins, Emilio, Anya, Hugo, Tiago, Val. Most of them have left the Institute, but I've been lucky enough that every time someone goes away, I get another chance to work with another person. And now we have Alex, and very soon we're going to have another person working on this project. And also, I would like to thank the rest of the team for the support and the discussions throughout these years. And again, thank you all for taking the time to watch this webinar. Stay safe.